Okay, so before we start 8.3, let's kind of quickly go over 8.2. 8.2, we had a population, we took a sample, we had a sampling size here, so we had P here, we had a P hat here, we had a sigma here, we had a sigma P hat, which ended up being square root of P hat 1 minus over N. And we did that. Okay, so now there were 3 specific conditions that had to be met. And what were they?
The large counts.
Okay, it had to be a random sample. Then you could not
Less than
oversample. And then there was the large counts and P greater than 10 and 1 minus P had to be greater than or equal to 10. Right? So those were the 3 conditions that we had to have. These 3 conditions had to be made for us to be able to go ahead and construct a confidence interval. And then we talked about interpreting a confidence interval. And we also talked about interpreting a confidence level. Okay? So those are the things that we kind of big picture wise talked about in 8.2. Okay? So 8.3, we're basically going to do the same thing instead of a proportion, we're going to go and estimate a mean. Okay, so basically it's going to be the same thing that we did before. We're going to have a mu, and we're going to have a sigma here. Over here, we're going to have an x bar. We're going to have a sigma x bar, right? And then we're going to do some stuff here, right? Okay, the same conditions are, well, mostly the same conditions are going to have to be met. This one's still going to be applicable. This one's still going to be applicable. Obviously, these cannot be applicable, right? Because we do not have a P or P hat anymore. Okay, we're looking at mu and sig and x bars here. Okay, so this is obviously not going to be there. But we're going to have something different, but we're still going to have a large counts here. Okay, we're still going to have a large counts prerequisite where we're going to have, we'll just call it large counts for now. Okay, all right. So let's go ahead and work on this. Okay, so the problem with 8.3, so the problem with population mean is that in the proportion, we were able to say that this guy was this. We don't have this anymore, right? So we don't have something that we can go and immediately say what sigma is here, what the sigma of x bar is, okay, all right? What we're gonna have is we're gonna have a sample standard deviation, right? So we're gonna have an S of x. We're gonna have a standard deviation from the sample itself, okay? But we don't know how this ties into this, okay? If we go back and we think about what we learned earlier, we said that we had something like this. Okay, remember this? We talked about this before. Now the problem is that before you do a sample, for the most part, when you're doing a population mean, this guy here is unknown. You are not going to know this. Okay, so this is our problem when we talk about a population mean, is that we do not know what the mean of, we do not know what the standard deviation of the population is going to be, okay? So we're gonna come our way with some clever ways to get around this, okay? So the way we get around this here, and when we talk about population mean, is that we are going to come up with a new distribution, okay? We are going to use what is called a T distribution, okay? And this was those tables that you went through. If you go back to the tables, go in the back of the tables, go back where the tables are, you go to T-1, If you go back, there are, I'm looking. So if you go to T-3 and T-4, or T-3, just T-3, T-3 says it is the T distribution critical values. It's a T distribution. So now we're gonna, so this was the T distribution stuff that was always next to our normal distribution stuff that we're finally gonna learn. Okay, so the T distribution is a distribution that kind of looks like a normal distribution. Okay, so let's say that this guy here was your normal distribution. If this is a normal distribution, okay, a T distribution is going to look like this. It's going to have fatter tails. It's going to have fatter tails and a lower peak. It's going to look like this. So this guy here is going to be your T distribution. Your T distribution would look like this. So we're kind of going to do the same mechanical stuff that we did before when we're doing a normal distribution, but we're just going to use a different T distribution, okay, the T distribution. So if you go to page 529, if you go to 529, it shows you the T distribution there, okay? There's a graph in your book. The solid black line, or is that the purple line or a black line? Looks like is that a purple line? Looks like a purple line. So the standard, okay, so the purple line is a normal distribution. Okay, if you look at now, there's a dotted line that says a T with 2 degrees of freedom. And then there's a green line that says T with 9 degrees of freedom. So in a T distribution, there was a thing called the degrees of freedom. Degrees of freedom. And the way you calculate the degrees of freedom is nothing more than it is your sample size minus 1. So if I had a sample of 10, that means that I have 9 degrees of freedom. If I had a sample size of 5, it means I have a sample size of, if I have a sample size of 5, that means I have 4 degrees of freedom. So if you go back to that T-3, let's go back to that T-3. If you look at it, T-3, it has on the very left column is DF. It is the degrees of freedom, right? It is the degrees of freedom, which we calculate using n minus 1. Okay, so the degrees of freedom from 1 all the way through what? What does it say? Braden?
Which one? 2 or 9?
Huh?
For which one?
So on T-3, the degrees of freedom are located at the very left-hand column, and your book shows degrees of freedom from 1 all the way through what? Were you able to find the page T-3?
Yeah, it's 1 to 3 point. Wait.
What?
Is it 1 to 636?
No.
1,000 or infinity.
Yeah, it goes to 1,000 infinity, right? There you go. So 1 through 1,000 infinity. So you can have sample sizes that are quite large here, okay? All right. So let's say so let's see, look at that table. So let's say that I ran a let's just say I ran a sample of where n was equal to, I don't know, 30. So n was equal to 30. That means that my degree of freedom is what? Is 29, right? So if you look at my degree of freedom of 29, the second, the very first column after the degrees of freedom says there is 0.683. That 0.683 means that if you go to the top of that column, it says 0.25, right? So in other words, I'm going to have 0.25%. So from here over here is going to be 0.25. So it's going to be 25%. This is going to be 25%, right? When my critical value there is 0.683. My critical value is going to be 0.683. Okay? And so what is a critical value? Let's go back to our book. If you go to the bottom of page 529, it shows you there how to construct an interval, a confidence interval, right? It has the X bar, because X bar is an unbiased estimator, plus or minus a T critical value, we just looked up, right? And it's going to have the S of X bar over square root of N. Okay, the S of X bar being the standard deviation of the sample, and then you divide it by the square root of the sample size itself, and then the critical value. We just found the critical value, okay? So that's how you're gonna do a confidence interval in your population mean, okay? So let's see if we can go ahead and do that. Let's go to flip the page and go to the example. This is page 530. Where am I at? Let's see if we can get Kyle back in again. Okay, so are you in, Kyle? Looks like he's finally in. Okay, so let's go to example on page 530. Problem, what critical value T star from table B should be used in constructing a confidence interval for a population mean each of the following settings? So A, 95% confidence interval based on a simple random size of 12. Again, so the simple random size of 12 is going to be what? So my degree of freedom is going to be what?
11.
12 minus 1 is going to be 11, right? So my degree of freedom is going to be 11. Now we're looking at the confidence interval here, right? So we're going to have, and we want what? What percent do we want? We wanted 95%, which means that on each end, what am I going to have? Each end I'm going to have 2.5%, correct? 2.5%. So I need to go to that T3 table, T-3 table, T-3 table. And I need to go to the degree of freedom as is going to be 11. All right, I need to find the 2.5 number. 2.5 is where? Looks like it's going to be the 2.201 number. 2.201. Everybody was able to find that? Was everybody able to find that? Was everybody able to go to their T3 table and find the 2.201 there? Okay, I hope so, because it's going to be on the test on Thursday. Okay, by the way, speaking of which, based upon what the titles are on this, so you have 8.1 was what? Our 8.1 was confidence intervals, the basics, and then 8.2 was the confidence interval for a population. 8.3 was the confidence or estimating population or confidence interval for a population mean. What do you think is going to be on the free response test? The test of free response portion of the test. Do you think that the confidence interval for a population and the confidence interval for a mean is going to be on the test? I'm pretty darn sure that's going to be on the test, right? Wouldn't it make sense for that to be on the test? Right? So you, at least you know that, well, two, there are going to be 3 free response questions. At least you know 2 of them are going to be. One of them is going to be calculating the confidence interval of a population. The other one's going to be calculating the the confidence interval of a mean, okay? And there's going to be something else. But at least you know what the 2 are, right? Okay. All right, so that's that. Let's get B. A 90% confidence interval from a random sample of 48 observations. Okay, so this is very important. So let's go to 48. So what's my degree of freedom? What's my degree of freedom? Anybody?
Wouldn't it be 40?
It'd be 47, right? 47, correct? The degree of freedom is 47.
Yeah,
Right.
but
So
there's
go to the actual page. If you go to the actual page, there is no degree of freedom here, okay? The degree of freedom. Okay, so now let's think about this. Let's go back to page 529. 529, as you can see, as the degree of freedom gets larger, do we get closer to a normal distribution or not closer to one? Do we get further away or closer to a normal distribution? What do you think based upon that figure in page 529?
You get closer because there's more samples.
Correct. You get closer to normal distribution because there are more samples. Exactly. So if you go to the infinity line of t distribution, you're basically looking at the same critical values as if you were in a normal distribution. That's why if you go to the 95% confidence interval, there's a 1.96 there, right? That one sounds familiar. The 90% is 1.645. That is also familiar because it's the same one we use in the normal distribution tables, okay? 99% is 2.576. These are all numbers that you used before, okay? So as the degree of freedom gets larger and larger, you get closer and closer to a normal distribution. So if you have a choice between going to either 40 or 50, because now our degree of freedom is 47, but I do not have a 47, you are always going to go with the lower number, which is more conservative. Okay, so you go with the degree of freedom that's going to read off the one that says 40. Okay, you're going to read off, so you're going to use the one that says 40 there. And if you do that, you're going to get 1.684. Okay? So now there's also a way to do this using your calculator, obviously, and that's on the technology corner on page 531. And it shows you how to use the inverse t, And this is basically finding the critical value for your estimation. You're trying to find a t star here, right? So if you look there, it says inverse t, so you go inverse t, and then you're going to write, then you're going to put in the value that you want, like 0.25 or 2.5 or whatever it may be, and then you're going to put in the degree of freedom after that, right? And it's going to give you what the critical value is. Okay, and that is in your second var stat, okay? So that's that. Okay, conditions for estimating your mu. Okay, same thing. We had the 3 conditions, right? I already gave you the 2. The first one was going to be the random sample. Second one was going to be you cannot oversample. You cannot oversample more than 10%. And the third one is your large counts. Now, the large counts is different. So what would you guess the large counts to be? When did we talk about large counts and we're doing a mean? We said that n has to be what? Greater than what?
30.
30, right? And that is from what? What was that from?
The central limit
The
theorem.
central limit theorem, right? Central limit theorem. So again, the first one is your first condition is going to be a random sample. Second one is that you cannot oversample, right? The third one is that n has to be greater than or equal to 30. Okay, now here's a caveat. Now, if n is less than 30, you can still use the t-distribution as long as the data is roughly symmetric, with no outliers. Okay? So if n is greater than 30, you're great. You already have the large counts. So you got 1, 2, and 3 are good. And you can go ahead and use the t-distribution to find the t star. And then you use t critical value there and do it. If n is less than 30, then you actually have to do a dot plot of the sample and look at the samples that you have and look at the dot plot and make sure it is roughly symmetric with no outliers. Okay, so that is on the top of page 533. Okay, the random sample, less than 10%, and then a normal sample, the large side, the large counts, it says, population has a normal distribution or the sample size is greater than 30. Okay, if it's a normal distribution, you're good to go. Okay, if it's normal distribution, you can go ahead and use the t-distribution if you are told that the population itself is normal. If the population itself is not normal, then, and if n is greater than 30, then from the central limit theorem, we know the sample is going to be normal anyway, so we're good to go. Okay, so if the population is not normal and your n is less than 30, then you have to do this. Then it says that the graph, the sample data, where is it? Okay, what? Okay, so if the population has an unknown shape and n is less than 30, use a graph of the sample data to assess the normality of the population. This is where we mean that assessing the normality is that we're going to say that if it's roughly symmetric and there are no outliers, we're going to go and assume that it is normal. Okay? So it also says, do not use the t procedures if the graph shows strong skewness or outliers, right? So it has to be roughly symmetric with no outliers. Okay, so let's go and do the example there. It says GPAs, wood, and SATs. Determine if the normal large sample condition is met in each of the following settings. A, to estimate the average GPA of students in your school, you randomly select 50 students. Here's the histogram. Okay. So in here, do I have to look at the histogram or what can I say here? I can say that n is greater than 50, right? N is greater than 50, so I'm good to go. Okay, so the large counts does work, right? Number 2, how much force does it take to pull wood apart? The stem plot shows the force, blah, 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 required to pull a piece of Douglas fir apart for each of the 20 random samples. So 20 random samples means that I'm less than 30 here. I'm less than 30, okay? I do not know whether or not the population is normal here. What I do know is that the data looks like what? What can I say about the data?
It's skewed.
It's skewed where?
The left.
It's skewed to the left, correct, right? It's skewed to the left. So therefore, it is not roughly symmetric and we cannot use the large counts. Okay, it says, so B says, no, the sample plot is strongly skewed to the left with possible low outliers and less than 30. okay? C, suppose you want to estimate the mean SAT math score at large high school. Here's a box plot, blah, blah, blah. And you have 20 students. So again, n is less than 30, okay? Is this roughly symmetric or not? Doesn't look roughly symmetric, does it? It is skewed to the what? Left or right?
Right.
Right.
Skewed to the right, right? Yeah, skewed to the right. Okay. Oh, it says yes. Box plot is only moderately skewed to the right. Oh, they're going to call this only moderately skewed to the right. Okay. All right. So that's a judgment call there. Okay. I can guarantee you on the AP test, they're not going to give you something that's even close. They're going to severely skew it one way or the other. Okay. All right. So we're going to have to worry about that. I would say that it looks like it's skewed right. Okay, I would not consider this to be roughly symmetric. Okay, all right, so there we go. And with that, we are done with the first portion. Okay, so let's go ahead and